How can Python handle concurrent database access without deadlocks? Imagine a busy restaurant where many diners are ordering at the same time. If the kitchen isn't organized, orders could get mixed up or stuck waiting forever. That's similar to what happens in databases when multiple applications try to access or change data simultaneously. Now, let's see how Python keeps everything running smoothly without causing those frustrating deadlocks. First, deadlocks happen when two or more operations wait endlessly for each other to finish, each holding a lock the other needs. To prevent this, Python applications need to manage database connections and transactions carefully. One way is by using transactions with proper isolation levels. These levels decide how much one operation can see or interfere with others. For example, setting the isolation level to read committed allows transactions to see only committed data, reducing the chance of conflicts. Another method is pessimistic locking. This involves locking specific data before making changes. Python can do this by executing SQL commands like select for update. It locks the selected rows, ensuring no other process can change them until the lock is released. This is great when you need to be sure no one else modifies data during your operation but can slow things down if overused. Optimistic locking offers a different approach. Instead of locking data upfront, it assumes conflicts are rare. Python applications check a version number or timestamp before updating data. If someone else changed the data in the meantime, the update is canceled or retried. This method allows more concurrency because locks aren't held for long. Modern databases like PostgreSQL, Oracle, or DuckDB use multi-version concurrency control. This system keeps multiple versions of data, so readers don't block writers and vice versa. Python benefits from this because it can perform many operations at once without causing deadlocks. When working with multiple threads or asynchronous code, Python needs to be careful. Each thread or coroutine should have its own database connection or cursor. Sharing connections can lead to conflicts and deadlocks. Using Python's threading or Asyncio libraries helps coordinate these operations safely. If a deadlock or conflict does happen, Python can catch the error and retry the transaction after a short wait. This retry logic is common in optimistic locking strategies and keeps the application responsive. In real-world CRUD operations, this means creating a new connection for each thread or coroutine, wrapping updates in transactions with retry mechanisms, and choosing the right locking method based on the situation. For example, when updating large amounts of data or inserting files like images, each thread can have its own cursor, perform the operation, and then join back together. In summary, Python handles concurrent database access without deadlocks by carefully managing transactions, choosing between pessimistic or optimistic locking, taking advantage of database features like multi-version concurrency control, and designing code that uses separate connections and retries when conflicts occur. This way, multiple users can work with the database at the same time smoothly and safely.